Do you ever wonder what happens when you use SSH to access a remote machine? Is the traffic really encrypted? What are those private and public keys that people talk about when they're using a secure protocol? In this video, we will look at different ways of running SSH and what's going on in the background to keep your data safe. So how do you access a machine remotely? In the old days, there were programs like telnet or putty, but those programs did not use encryption, so anyone on the network between these two computers can see that data. Those programs have now mostly given way to a more secure method called SSH, which is short for Secure Shell. Using SSH, we can access a remote machine, but the data that goes between the two machines are now encrypted. Let's take a look at what happens on the wire when we use telnet. Here I have a Kane server running the SSH daemon, and I'm going to run Wireshark and monitor the Ethernet port, which here is named ENP0S3, and then show you the traffic. To limit all the noise on the network, I'm going to filter and only look at traffic from our client machine at IP 192.168.1.158. Now back on my client machine, I will run the hostname command just to show you that we are on the client machine named Paladin. Then I will use the telnet program to log into the server at IP 192.168.1.164. I'm greeted with a login prompt, and you probably noticed that the other window here where Wireshark was running, it has started to capture quite a number of packets. Let's continue to log in to the examiner account with the proper credentials. And all this time you can see Wireshark capturing more packets. Now my client has logged into the server. We can see the login banner telling us that we are on the Kane distro. We also see the prompt change to let us know that we are now the user named examiner, and we are on the machine named demo server. I'm going to type in the hostname command just to prove again that we are now on the machine named demo server and not on the Paladin client anymore. After that confirmation, I'm going to cat the system password file at etc password. We see the contents of the file fly across the screen. And now I'm going to look at the etc shadow file, which contains the hash passwords, and that file also flashes across the screen. All right, let's go back to the server and look at the Wireshark capture. After selecting one of the packets, I'm going to right-click for the menu and then select the follow option for the TCP stream. Now I see the entire stream of packets between the client and server. We can see the login prompt where the account name is displayed, and then every character that I typed is actually displayed twice. This is because when we type the letter E, it is sent across the network to the server, which is then echoed back to the screen. Then we see the password of password being typed in. Note that since the password is not echoed to the screen, we only see the letters once. So the big takeaway here is that if someone is sniffing on the network, they can easily see the login and associated password go by in the clear, completely unencrypted. So this is definitely not secure. Continuing on, we can see that the text that went to the client screen is captured here as well. Right, so as we scroll down, we can see where we typed the hostname command. Once again, each letter is repeated because as the characters are typed on the client machine, each character is sent over the network to the server, which is captured and then echoed back to the client to be shown on the screen and is captured again. And we see the response from the server to the hostname command by the word demo server. The next thing that I did was to type the cat command to look at the file etc password. You can see that the command being captured and echoed, and then the content of the file is sent across the network. And all this content is captured by Wireshark. Lastly, I typed the command to sudo cat the etc shadow file. As you can see, I started to type the word shadow, but misspelled it with SHWA. Then you can also see that Wireshark captured two backspaces as represented by the .. bracket K. Right, so this is going to backspace twice, And then it's going to be followed by the remainder of the correct spelling of shadow with ADOW. And then the contents of the shadow file are subsequently displayed on the screen. So the summary here is that with telnet, nothing is safe. Everything is in the clear, including the login credentials and the content of sensitive files that are coming across the screen. To contrast this with SSH, I'm going to reset Wireshark so that it is capturing traffic from the client machine again. But this time, instead of using telnet, I will be using SSH. And much like telnet, as soon as I start the program, there are packets being captured by Wireshark. So I'll go ahead and type in the password to log in, and then typing the command hostname to verify that we are on the server. And then lastly, I'm going to cat the etc password file. Now let's hop over to Wireshark and see what we got. And again, I will follow the TCP stream. So what we see here in the beginning is the client, which is in red, sending its information that it is using SSH 2.0 and OpenSSH version 7.7p1. Then the server, which is in blue, sends back that he is using SSH 2.0 and OpenSSH version 8.9p1. And then the client sends over a list of his supported protocols like Curve 25519, SHA-256, etc. And the server sends over a list of his supported protocols. And then it looks like they settled on using the ECDSA SHA-2-NISP-256 protocol. And then they continue with the conversation, all completely encrypted because we can't see the hostname command, we can't see the cat commands. It looks like it's all just gibberish to me. So it seems like SSH is doing a good job, at least not making it easy for an attacker to snoop the network for data. All right, so what do you need to run SSH? Well, you need two pieces of software. First, you will need the SSH client software, which pretty much comes with most Linux machines and all Macs. If your Ubuntu-based distro does not have the SSH client installed, you can do sudo apt install OpenSSH-client. On a Windows machine, you can use PowerShell, which has the SSH client already included, or you can download a GUI like PuTTY. Once you have the client software, then the second thing you will need is a server that can talk SSH. On a Linux system, you can verify by typing sudo systemctl status ssh. And so you can see here on this machine, the status of SSH is that it is running, which means the server is installed and enabled. And if your Ubuntu-based distro does not have the SSH server loaded, you can install the server by running sudo apt install OpenSSH-server. And then once you have the software downloaded, to turn on the server, you can do sudo systemctl enable SSH. Now that we have the software on both the client and the server, we are ready to use SSH. The basic method of using SSH is to sign on to the remote system with a password. And so the assumption is that you have the credentials of the remote account. The command consists of calling the SSH program, then telling SSH the account name and machine name of the remote system. So for example, you can say david@myserver.mydomain.com, or you can use the IP address like examiner@192.168.1.164. And because this is the first time we are connecting to the server from this client, the SSH program will cause a prompt to come up about a ECDSA key fingerprint and ask whether you want to continue. If you answer no, then SSH terminates and you get your command prompt back and nothing happens. If you answer yes, this will cause a file named known host to be created in the SSH folder on the client machine. And then it adds the server fingerprint to that file so that it can be authenticated in future logins. So once you've successfully logged in, you are essentially on the server machine and can perform whatever tasks you want to perform on that server. Most people just blow by the ECDSA key fingerprint notification that we saw earlier, but I want to take a few moments to get a closer look at what this is about. ECDSA stands for Elliptic Curve Digital Signature Algorithm, which is used to authenticate the remote host so that you'll be alerted if the remote ID has changed, possibly due to a man-in-the-middle attack. To see what the fingerprint is on the server, you should physically get on the server as opposed to remoting into it, and then type in ssh-keygen-lf/ssh/ecdsa_key.pub. And you should see that this matches with what was presented to us when we first tried to SSH over. And this confirms that we are indeed SSHing into the server as opposed to a man-in-the-middle server. Once you've done this once, the fingerprint of the server will be written to the known host file, and any subsequent SSH sessions, this fingerprint will be checked. If the fingerprint changes, as we can see here in this demonstration, it says remote host identification has changed. So what this could mean is that the server has either changed their public key or you have connected to a different machine, which is possibly due to your DNS being hacked, and then you're pointing to a bad guy machine where they're intercepting and rerouting your SSH connection to steal your passwords and data. So basically pay attention to what you see on the screen. That's great that we can log in via a password, but there's a second and better way of using SSH. That is by using key pairs. What's a key pair? Well, it's a method of asymmetric cryptography that uses two separate but related keys to encrypt and decrypt information. SSH uses these keys to establish proof of a client's identity to the server. So by using key pairs to perform the authentication, the process does not use passwords, which eliminates the risk of transmitting the password over the network and also the risk of using simple passwords or blank passwords that can be easily cracked by brute forcing. SSH servers usually invite sign-on attempts for password guessing, and this method dramatically reduces the chances that the attacker correctly guesses the keys. Hosting companies usually recommend this method of using key pairs over the use of passwords. But note that the risk now is on securing the private key, which is just a file. So let's generate some keys. Note that we do this on our client machine, not the server. The program that we will use is called ssh-keygen. And the program needs a few options to be specified. But let's run it in the interactive mode first to see what the options are. The first question is the path of where to save the key. So the default is to save it in the hidden folder named .ssh in the user's home folder. And then it will use the name of id_rsa. If the folder does not exist, it will be created for you. So I'm going to name my key /home/blue-monkey4n6/id_rsa_demo. One thing to note is that unfortunately this program does not recognize the tilde, which as a shortcut to your home folder, so you actually have to type out the entire path. Next, it will ask for a passphrase. The passphrase is used to encrypt your private key to protect it from being stolen and used by unauthorized parties. You can choose not to use a passphrase by just hitting enter. Once you enter the passphrase twice, the program will give you a fingerprint of the private key and then a random art image. These are interesting, but we will come back to them later. If we did a listing of the .ssh folder, we will see two files. The private key named id_rsa demo, and then the public key with a .pub extension at the end. If we take a look at each file, starting with the private key, I'm going to do cat.ssh/id_rsa demo. As you can see, the file tells you that it is a private key on the top here, and it also tells you that it's a private key on the bottom. Now let's take a look at the public key. I'm going to do cat.ssh/id_rsa_demo.pub, and basically it's just a bunch of letters. If you're automating the ssh-keygen process, then you will want to type out a longer command that contains what you would have typed in with the interactive mode. So the first option is the -t for the type of key that you want to generate. Your choices are RSA, which is the default, DSA, ECDSA, ECDSA-SK, ED25519, and ED25519-SK. The selection of the best type of encryption algorithm is beyond my brain capacity, but I have read that the ED25519 has better performance, although not as universally supported by RSA. But since I'm using this in my systems where I know that ED25519 is supported, that's the one I'm going to be using. The next option is the -f option to specify the path name of the output key file. So once again, I am going to put it in my .ssh folder, and for this one, I'm going to name it id_ed25519_demo. When I hit return, the program once again will ask for a passphrase, to which I'm going to leave blank this time. The program has created a key pair in the .ssh folder where I told it to do so. So I'm going to go ahead and do an ls on the .ssh folder to look at anything that starts with id_ed25519_demo. So again, we see the two files. One is a private key, and then one is a public key. So let's take a look at the private key by doing a more of .ssh/id_ed25519_demo. There's our private key. And similarly, I'm going to look at the public key by doing a more .ssh/id_ed25519_demo.pub. And there's our public key. Now that we created the keys, we need to deploy the public key to the server. But before we actually do that, let's take a look at the server and look at the home folder of our user examiner. I'm going to do an ls-al of .ssh. Notice that there is no folder named ssh yet. So let's go back to our client machine, and then let's copy the public key to the server using a tool named ssh-copy-id. So I'm going to go ahead and type in ssh-copy-id, and then specify the option of -i to see which file to send over. So the one that I'm going to use is the .ssh/id_rsa_demo.pub. Make sure you're sending the public key, right? So the .pub is important. And then the destination is going to be the examiner@demo server. Next, we see that the system is trying to install the key, and the server prompts us to enter the password of the remote user we specified. So I'm going to go ahead and enter the appropriate password, and then we complete the copy. The last thing that ssh-copy-id tells us is to try logging into the machine using SSH. Well, let's go ahead and do that then. So I'm going to do SSH, and then I'm going to specify the key to use. So -i.ssh/id_rsa_demo, and then finally examiner@demo server. So now you'll be prompted for the passphrase that you use to encrypt your private key when you set it up. Once again, understand that this is the passphrase for the key, not the password for the account. So there are two different concepts. And this passphrase is not transmitted over the network to the server. It is just being used locally to decrypt your private key and then using that to perform a handshake with the server. And once again, you're not using any passwords for the remote system. And now you're on the server. If the prompt and other information on the screen doesn't indicate to you that you're on the server, we can type the hostname command and see that we indeed are on the server named demo server and no longer on our Paladin machine. Since we're now on the server, let's take a look at what the ssh-copy-id command did. Let's run ls-al of .ssh. So now we can see that there's a new folder where there wasn't one before. And inside the folder is a file named authorized_keys. Let's take a look at the content of this file by just doing a cat of .ssh/authorized_keys. We see that there's one line in this file with 3 sections delimited by a space. The first section is the key type used for the attached key. In this case, we're using the RSA algorithm, so that's what it says. And in the second section here is the base 64 encoded public key. And the third section is the comment section where the name of the user who created it is placed. The comment field is not really used by the SSH program, but it's good for the humans to differentiate different keys because you can have more than one key in this file. And if we exit from the server and look at the public key on our client, we'll notice that the keys are identical to show that the keys were properly copied over. Now I'm going to do this again. I'm going to copy over a second key, the one that we generate with no passphrase, so you can see the difference. So I'm going to do ssh-copy-id-i .ssh/id_ed25519_demo.pub. Once again, make sure you're only copying over the public key and not the private key, right? We have to basically protect those private keys very carefully. And lastly, the destination is examiner@demo server. So now we can use SSH to access the remote server by typing ssh-i.ssh/id_ed25519demo and then examiner@demo server. So we have to specify the -i because we have to tell it which key to use. Otherwise, it's going to default to the key that's the RSA key, which we did not generate. So that's going to fail. And notice this time we did not encounter any prompts asking us for the passphrase because we did not use one for this particular key. Now that we're heading down the path to make things more secure by using the key pair to log in instead of the password, let's take the next step by disabling the login via password. So in the server, we're going to edit the SSH server configuration file. So I'm going to do sudo vi/etc/ssh/sshd_config. And I'm going to search for the phrase password authentication. And then I'm going to change it to a no at the end of the line. Now, one thing to consider is to make sure that your keys work before disabling root login. Otherwise, you may never be able to get back on the machine. And you may also want to add your account to the sudo or wheel groups before you disable root login via the password so that you can perform system administrative tasks with your other account. So the way to do that is just type groups to see what groups you're currently in. And if your user is not in the sudo or wheel group, you can add them by doing sudo usermod -a sudo examiner. And after you've made these changes to the configuration file, you'll have to reload the SSH server before they take effect. So let's go ahead and do sudo systemctl reload ssh. Now, if we try to SSH from the client to the server, we can do ssh examiner at demo server. So this will basically get a permission denied error because we're not allowing passwords. But we can still use the key pairs to gain SSH access, right? So if we do ssh-i .ssh/id_ed25519_demo examiner at demo server, we are able to get right in. And because we're using the key pair, we don't need to type in any passwords. Another way to secure the SSH server is to change the default SSH port from 22. Yeah, the attacker can easily use nmap to find a new port, but at least that's slowing them down a little bit. And to check on the port, we can use the netstat command. So netstat-l4nt, and we see that port 22 is listening. So to change the default SSH port, we will edit the config file again. This time, look for the line with the word port, and it's defaulted to 22, so I'm going to change it to something else. I'm going to change it to port 60022. And if your config file doesn't have a line with the port, you can just add it, and again, just specify a different port like 60022. Okay, so I'm going to go ahead and save and quit out of VI. And since we updated the config file, we need to reload it again. So sudo systemctl reload ssh. And now that we've updated the server, let's go ahead and rerun netstat-l4nt. And this time we no longer see port 22 as a listening port, but we do see 60022. And let's go back on the client machine and try to SSH over to the default port. So I'm going to do ssh-i.ssh/id_ed25519 examiner at demo server. And this is going to fail with the connection refused error because by default our client is going to port 22, which there is nothing listening there. So let's do this again by just doing an up arrow and then adding the -p option to specify a port of 60022. And sure enough, we are back in. The Secure Shell Protocol, better known as SSH, is a cryptographic network protocol that allows network applications like remote logins and file transfers to perform securely over an unsecured network. We learn how SSH uses public key cryptography to authenticate the remote computer and then allow it to authenticate the user if necessary. We saw the communication channels using public-private key pairs to encrypt a network connection. And then we also play with how the SSH server can be secured in different ways, including eliminating password authentication and also changing from the default port it operates with. For more videos about networking, watch these videos here. Make sure that you click on the blue monkey to subscribe and get notifications for new videos. Thanks for your time and happy hunting.